Yes, hello.
Okay, you should now also see my screen. Okay, and we were trying to understand the basics of quadratic forms that are the most simple, most elementary case of let me record it. The most elementary case. Okay. Quadratic forms are the most elementary case of nonlinear functions in many variables, in particular in two variables. Okay. So, one, I'm trying to just recap the basic points. One important point is whether an expression that corresponds to a quadratic form, which of course depends on many variables. The variables here are called h1, h2, hn, but in principle they could be x1, x2, xn. Whether a quadratic form preserves the same sign, for instance, it is always positive, or it is always negative, whatever the values of these variables are. Because remember that the quadratic form has this expression in two variables. Of course, it depends on coefficients a11, a12, a21, a22 of this matrix, which is supposed to be symmetric. Okay? Symmetric means that this element a12 is equal to a21. Otherwise, we have other kinds of quadratic functions, but they don't have the properties of quadratic forms. Okay? So this is a quadratic form in two variables. This is written with matrix. All this seems to be very unclear. What is the quality of the audio? Please give me some feedback. How's the quality of the audio? Okay, let me change the microphone. Okay? So I'm going to the settings, and now I'm trying to use, is this the reader? Let me use this one. Let me turn this off. And what about the quality of the audio now?
It's better.
Better? Okay. Okay, so better to use the other microphone, which is the Jabra, called Jabra. Okay, I will use this one. Okay. And I was saying that this is supposed to be a symmetric matrix. This is a quadratic form in two variables. Remember that these a11, a12, a22 are numbers. So it depends on the variables h1 and h2, right? In some cases, it has a very nice property. Whatever the values you select for this h1 and h2, this quantity is always positive, for instance. Or in other cases, it is always negative.
or in other cases, it is always non-negative or non-positive. But there are some cases in which the sign of this quantity depends on the values that you select for H1 and H2, okay? But if we are in these cases in which this function of two variables preserves the same sign, independent of your choice of H1 and H2, we are in one of these four cases. And the name of the case is clear. The meaning is inside the name already. Positive definite quadratic form means that you can select any value for the variables H1 and H2, or also for the n variables H1 and H2 up to Hn, and the quantity is always positive. And this is called positive definite quadratic form. If it is always negative, it's called negative definite quadratic form. Then there are the weak definitions. They are the same but weaker. It's positive semi-definite if it can be zero, but it cannot be negative, okay? It is positive or zero. Negative semi-definite if it cannot be positive. It is always negative or zero. Of course, in these definitions, you have to exclude here h equal to 0, because for h equal to 0, any quadratic form is 0. Just replace 0 and 0 to h1 and h2 here. It becomes 0, okay? So for any quadratic form, q of 0 is 0. What really matters is the behavior for values of the variables which are not all 0. And we have these four cases. And the very important remark here is that positive semi-definite quadratic forms are the simplest examples of convex functions. Negative semi-definite quadratic forms are the simplest example of concave functions, okay? Why? Because they generalize the positive semi-definite and the negative semi-definite generalize in 3 dimensions what is the parabola in 1 dimension, okay? I'm trying to show you a bad quality picture. For instance, remember you have 3 axes, right? This one. And this is the correct one. You have 3 axes, one to represent the surface. So, for instance, you have your axes are like this. You have x axis, the y axis, and these represent the two independent variables. And then you have the z axis, which represents the value of the third variable. Okay, I'm trying to represent a negative definite quadratic form. Remember that all are 0 when the values of the variables are equal to 0, okay? So a negative definite quadratic form could be like this. Of course, this is dashed because it is supposed to be below the base plane, okay? And then it has, of course, it's not a parabola because it is a surface, but look, it is like this, okay? So it's like a paraboloid like this one in 3 dimensions. This is the simplest example of a negative. This is a negative definite quadratic form, which is similar qualitatively to our parabola, having the vertex in 0, which is ax, okay, squared. F of x is equal to ax squared, where a is negative, is a parabola like this. And this is similar in 3 dimensions. Is that clear? And this, but of course, what matters here is the coefficient a in 1 dimension. And a is negative here. Here we don't have a coefficient. We have 4 different coefficients, actually 3 because the matrix is symmetric. And there must be some formula aggregating these coefficients that makes this surface to behave similarly to this one. It is called negative definite in this case, if the coefficients satisfy that particular property, okay? that we have already seen last week, and the property is this one. If the elements in the main diagonal are negative and the determinant of the matrix is positive, then we have a negative definite quadratic form, and it looks like this. So it's clear what is a positive definite quadratic form. I use a different color here. A positive definite quadratic form would be this one, okay? It is worth 0 at 0 when x and y are equal to 0. This is 0, but otherwise it is positive, okay? So it's similar to this one. Nothing difficult. But the point is that we cannot define the coefficients negative. What is the meaning of negative? There are 4 coefficients in the matrix, okay? So there is a rule for aggregating all of them and having a behavior which is similar to a negative coefficient in a one-dimensional parabola, okay? It's very simple. And another important point here with these pictures, let me say something about this. Clearly, if you have a positive definite quadratic form, which is worth 0 here, but elsewhere it is worth a positive value, like this one, clearly 0 is a minimum point for this surface. Is that clear? So it is the simplest example of a convex function which has a minimum in 0, by definition in this case. And also, if it is negative definite, 0 is a maximum point for this surface, okay? It's the point in the domain where the surface reaches the maximum level as measured on the vertical axis, okay? These are the main points about quadratic forms. Next, just a moment on these bad quality pictures, but you may have another situation in which you have a positive definite quadratic form plus a constant. It's like a parabola, like this, plus a constant, okay? So we may have something like this in 3 variables. No, this is not good. We may have something like this. Now, of course, the minimum is not in 0, but it is in the value of that particular constant. Is that clear? A quadratic form plus a constant, when the variables are 0, the value of the function is that constant that increases the level of this surface, okay? So and also you will see that when we have a quadratic form, like for the one-dimensional parabola, we may have a minimum or a maximum also when we add a linear term and a constant term. The same for a quadratic form. If the quadratic form is negative definite, we will find a minimum also if the quadratic form is like this. Quadratic form, which is supposed to be negative definite, plus a linear form, b1x1 plus b2x2 plus b3x3 and so on, plus a constant. So this is the equivalent of the parabola in one dimension. The quadratic term, the linear term, the constant term, okay? And if this doesn't matter on the behavior. If this is negative definite, okay, you will find a minimum here. If this is positive definite, sorry, if this is negative definite, you will find a maximum. And if it is positive definite, you will find a minimum. So basically, the existence of the maximum and the minimum for these surfaces is preserved also if you add constant or a linear term and a constant. And that would be very important because they are the simplest possible examples of parabolas. Of course, if you don't add the term in x, you have something which is centered around the vertical axis, like in the one-dimensional case. If you add the linear term, what happens? Remember the elementary parabola, you shift this surface on the right or on the left, okay? It's very similar to the one-dimensional case of the parabola. And these are the simplest possible functions Two variables, for instance, having a maximum or a minimum, provided that they are negative definite, positive definite, or at least negative semi-definite, positive semi-definite, okay? Okay, so this was my main point. It's important that you train your intuition with quadratic forms because next, everything, finding the maximum or the minimum of two variable functions just means approximating these two variable functions with a quadratic form and then finding the maximum and the minimum of this quadratic form, okay? Is that clear? So we use second order approximations of two variable functions. So it's important to understand the quadratic form. These are the definitions, not the definitions, the rules to conclude whether a quadratic form is negative definite or positive definite, or negative semi-definite or positive semi-definite. Okay, the coefficients in the main diagonal are both negative and the determinant of the matrix is positive, it is negative definite. Coefficients on the main diagonal are both positive and the determinant is positive, like the previous case. We have a positive definite quadratic form. If we have the same inequalities but weaker, that is with the possibility of zero included, then we have respectively negative semi-definite and positive semi-definite quadratic form. Okay? Negative definite are strictly concave. Positive definite are strictly convex. Negative semi-definite are just concave. Positive semi-definite are just convex. Now, in the one-dimensional case, we don't have this distinction between semi-definite and definite. So it's peculiar to the multivariable case. I will try to show you some examples now. But anyway, the idea is that this is, for instance, positive definite, but suppose that you have something like this. You don't have only one point where it is zero, for instance, the origin, okay? You have a full line of points where this is zero, okay? So you have a surface, these are several sections of the surface, which doesn't have a unique point where it is zero, but it has a full line of points where it is zero. This is an example of a positive semi-definite. It's always positive, but there is a line along which it is zero. I hope this is clear. It's not like, it should be clear. It's not like a cup, okay? It's like this. Along every section, you do have a parabola, but you have a full line in which this surface touches the horizontal axis, the base plane, okay? It's not difficult to figure out. Okay, so this is an example. This is, of course, a symmetric matrix. Look at the elements in the main diagonal. They are both positive. Compute the determinant. Remember that the determinant of a matrix, which is it is a general concept, but in the case of two variables can be computed as the sum of the elements in the main diagonal, 2 times 3, minus 2 times 2, minus the sum of the elements in the other diagonal. So it becomes 6 minus 4, it is 2. It is positive. Of this quadratic form, at least the quadratic form associated to this matrix is positive definite, okay? Based on the previous definition. This means that you can build the corresponding quadratic form and give to H1 and H2 any value, and you always get a positive result. Okay, look at this one. The matrix has the two elements in the main diagonal, remember that we already learned how to switch from a quadratic form to the corresponding matrix, okay? So just look at the elements in the main diagonal are -1 and -1 here, and then you have to take half this mixed coefficient, and this is the element in the other diagonal, okay? Here the determinant is 1, -1, 0. It doesn't fit in the definition of negative definite, but it does fit in the definition of negative semi-definite, okay? So it's always negative or 0, and it is 0 not only in the origin, but also there is another set of points in the domain where this quantity becomes 0. And it's easy to see how it works here, because you can just rewrite this in this way, and this is just minus x minus y squared. But this means that, okay, 0, 0 is a point where this is 0, but any other point where x is equal to y is a point where our quadratic form will be 0. And this is basically the bisector of the first quadrant, okay? Along that particular line, it's like this, okay? Along that particular line, we have a surface like this one, which is a parabola if you take any section, but along the bisector, it is 0. Okay, this is another example of a negative definite, because this is minus minus, and this becomes plus 1/2 minus 1 over 16. It is positive, the determinant, it is negative definite. Of course, this, I want to point out one thing. These are general definitions. We are only defining what positive definite means for a quadratic form. This holds for 2 variables, 3 variables, 200 variables, okay? But this is a characterization of this, a way to test whether it is positive definite or negative definite. And of course, it is strictly related to the two-dimensional structure, okay? There are analogous theorems for 3 dimensions, 4 dimensions, but they are much more complicated. So, I mean, the relations that must hold between the coefficients are not as simple as these ones, okay? But there are ways to characterize also in these more general cases whether quadratic forms are positive definite or negative definite or whatever by just looking at the coefficients of the matrix. Also, if it doesn't fit into any of these cases, it is called indefinite, indefinite, otherwise it is indefinite. Indefinite means that you can find at least one point in the domain where it is positive and at least one point in the domain where it is negative. So it doesn't correspond to any of these definitions. And also another important thing, which is just, I mean, notation, definition, nothing difficult. Sometimes in the textbooks, but also in this course, we will call positive definite the quadratic form, or just positive definite the corresponding matrix. So when I say this matrix is positive definite, this just means that it is a symmetric matrix, of course, and the corresponding quadratic form is positive definite, okay? Because there is a 1-to-1 correspondence between a symmetric matrix and the associated quadratic form, okay? So if we start from the quadratic form, you can reconstruct the matrix. If you start from the matrix, you can obtain the associated quadratic form. Clear? So we use this for any of them. So concavity in general, I hope that your intuition now is, everything is intuitive, and there are many ways to define concavity. The most general, which is compatible with the level of this course, I mean, and this is already very general, is this one. I give you the definition for n equal to 2, but it can be generalized immediately to any n variables. We must have a function f of x1, x2, which is defined over a convex set. Do you remember what a convex set is? Convex set in the plane A function here is a function of two variables, so the domain is a portion of the plane. In the plane, we must have a convex set, and this means that our domain must be a convex set. This could be the domain, the whole plane could be the domain. This one could be the domain, but this one is a domain that doesn't apply to the definition. It doesn't allow a definition of a concave or convex function. Okay, this is not a convex set in the plane. This is a set for which you can find 2 points. You join them, and part of the segment falls outside of the set. So it's not really. It doesn't make sense trying to define convex or concave functions if the domain is a set like this. Okay, the domain must be a convex set. Okay, if the domain is a convex set, we say that this function f of x1, x2, x1, x2 is the name of the two variables, y is the name of the third variable now, is concave if the set B of the points x1, x2, y that belong to the three-dimensional space such that y is below the surface defined by the function is a convex set. So this is the definition of a concave function, okay? Take the function, this is the surface representing the function. Consider the points not on the surface, but below the surface, see? Less or equal to below the surface. Is that a convex set? In the space, of course, not in the plane. Yes, it is, because it's intuitive that if you take any 2 points, you join them, you get a full segment that belongs to the set, that is a full segment which is below the surface, okay? Clear? Now this is a concave function. Look at this one, this is not concave. Okay, in the domain we have this, let's say this common domain. The domain could be, of course, it must be a convex set, but if you look at the surface, the set of points such that y is less or equal to f of x1, x2, that is the set of points lying below the surface, is not a convex set. You can take 2 points here. It's possible to select 2 points, to join them, and having part of the segment lying outside. Outside means lying above the surface. Clear? Okay, so this is the most general definition of a concave function. What is the definition of a convex function? It could be like this with the inequality reversed, in particular this one. We should write here is convex if the set B of points blah 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 such that y is greater or equal to f of x1, x2 is a convex set. This remains convex set. But the most common definition is don't worry about convexity, focus on concavity. F is convex if its negative is concave, okay? So the negative of a concave function is a convex function by definition. Now, what is the point here? The point is that, okay, nice pictures. I understand what is a concave and a convex function, but are there practical tools to understand immediately whether a function is concave or convex, at least for common functions? We have a range of rules. Here are the most common ones. And you will see that, I would like to say, 75% of our examples will fall within one of these cases. Okay, so these are practical rules that work with common functions. And from these you can immediately understand if your function is concave or convex. One is very trivial. A negative semi-definite quadratic form is concave. We know this already. Okay? A negative semi-definite quadratic form is concave. So don't try to test for concavity with other tools. if you recognize that this is a negative semi-definite quadratic form, this is concave. There are important examples in, and of course, a positive semi-definite quadratic form is convex, okay? I only focus on concavity, but just reverse the statement. A positive semi-definite quadratic form is convex. There is in one of the oldest models of modern financial mathematics is the portfolio selection model. It is based on a positive definite or positive semi-definite quadratic form, which is the variance of the return of a portfolio, which has to be minimized, okay? And this is an example. Other examples in statistics and econometrics are quite common, okay? In its general form, finding that in the linear regression, applying the least squares to obtain the coefficients of the straight line that approximates the data, okay, is a matter of minimizing a quadratic form, okay? And this quadratic form is positive definite or positive semi-definite. So these are there are common cases in applied mathematics to economics, to statistics, in which we have positive semi-definite quadratic forms, or even negative semi-definite quadratic forms in other cases. Another example, which is very important for our applications, a Cobb-Douglas function. Cobb-Douglas is a power function in two variables. Its general form is like this. Of this type, y is equal to capital A positive, x1 to the power of alpha, x2 to the power of beta, where x1 and x2 are two positive variables, and alpha and beta are positive coefficients, is concave, provided that the sum of the two exponents, alpha plus beta, is not larger than 1. So they must be positive. If their sum is not larger than 1, it is concave. If it is strictly smaller than 1, it is strictly concave. So it's very easy to remember this, okay? These are two very important criteria for common functions. There are more general criteria. A concave function on one variable is concave also when it is regarded as a function of two variables, or more generally of n variables. Not sure that you can get it immediately with some geometric intuition. If not, of course I don't want to try, but look at this. This is not the case. This one is the case. This is another tool to quickly understand what's going on. Okay? This is a function of two variables, which is the blue one. The log of 1 plus x. In principle, this is a function of one variable, okay? But I could consider this as a function of two variables. Log of 1 plus x plus 0 times y. Okay? If I regard this as a function of two variables, this is not a line in a plane. This is a surface in the three-dimensional space. But if you, okay, so this is the x-axis, this is the y-axis, and this is the z-axis, okay, the vertical one. Can you see that this is in fact a function of only one variable, because whatever is the value of the second variable y, you only get the same curve, okay? Is that clear? Okay, so the function of two variables, the function of one variable is regarded as a function of two variables. The function of one variable which is concave, is concave also when it is regarded as a function of two variables, and this is very clear from the graph. So, for instance, if I don't tell the software that this is a function of two variables, I'm not a specialist of GeoGebra, but anyway, that shouldn't be difficult. If I don't tell that the function is two variables, but I just write the log of 1 plus x, I get just a curve, okay, in a plane. Clear? Otherwise, I get the surface. But along any sections, there is the same curve. Okay, so this is, and this is important because sometimes we have a function of two variables, like this. F of xy is equal to, for instance, the square root of x plus the log of 1 plus y. These functions are very common in applied models, also in economics. It's a sum of different terms, and each term depends on a unique variable. This is called additively separable. Okay? For instance, you may have, in some cases, there are models in macroeconomics in which you have a function like this. It's u of x1 plus beta u of x2. It's not, let's call it c1, c2 plus beta squared u of c3 plus beta to the power of n u of cn. And this is capital U of c, where c is a vector, c1, c2, cn. This is a function of n variables. Each, for instance, in most common models, this u is a concave function, for instance, a utility function. And this would be the utility from, there is a time horizon of n periods. This is a consumption in the first period. C2 is the consumption in the second period, and so on and so forth. And Cn is the consumption in the last period, okay? The utility of this consumption plan is the sum. In many models, it is additively separable. So it is the sum of the utilities of consumption in each period, but future utilities are discounted, so are reduced in their entity, in their value, because beta is a coefficient between 0 and 1. It is a discount factor, okay? So the larger, the farther in the future is the time period, the more the discounting, okay? This is an example of an additively separable function in which we have the sum of different concave functions of n different variables. This is a basic example, okay? But based on our rule, we can be sure that this is a concave function. Why? Because you will see that this is a concave function of variable y. This is a concave function of variable x. These are very elementary functions. You can test concavity by using the second derivative because they are one variable function. These are also concave functions of two variables, okay, because of the previous rule. And you will see the next rule, the sum of two concave functions is itself a concave function, okay? So we can be sure that this is concave. This is just to illustrate that these simple rules are very powerful and allow you to resolve a lot of cases a priori, so without investigating the second derivatives or other tools like this, okay? So this is the most important thing. Another rule is that linear, more precisely affine functions are both concave and convex. A function which is linear, affine means linear plus a constant. In principle, linear is only the part a1 x1 plus a2 x2. If we add a constant, this is called affine, but economists do not use affine, they always call them linear, okay? But in principle, from a mathematics viewpoint, affine is linear plus a constant. but you can forget it. Just remember that the affine is linear, okay? This is both concave and convex. What is the shape of this function in the three-dimensional space? This is a plane. So basically, a plane has no concavity, no convexity, right? It is a plane. It is considered both concave and convex. Then, if you have the sum of a concave function plus a plane, this is concave, because this can be regarded as both concave and convex. And this is the most powerful one. A sum of concave functions is concave. This can be proven very easily, also in general. And another one is that a concave transformation of a linear function is concave. For instance, if you have the plane as above, okay? A1x1 plus A2x2 plus B. And then you take the square root of G is a concave function of one variable. Then what you obtain is concave, okay? Remember that you can reverse all of these statements. The sum of convex functions is convex. A convex transformation of an affine function is convex, okay? A convex function of one variable is convex also when regarded as a function of two variables or n variables. So you can reverse all of them. Look at this example. This is already, I mean, one step further, but there is another way to check for concavity of two variable functions, and we can be sure. Remember what we said about quadratic forms, okay? Now, take a function of two variables, compute the Hessian matrix. If you discover that the Hessian matrix, which in general will depend on both x1 and x2, okay? If this matrix is negative definite for any x1, x2 in the domain, then you have a strictly concave function. If it is negative semi-definite for any x in the domain, you have a concave function, okay? So basically, another way to check for concavity, convexity, is to look at the Hessian matrix of the two variable functions in our case. If in some cases it is possible to show that the Hessian matrix is positive definite or negative semi-definite or positive semi-definite for any point of the domain, not just at a specific point, for any point of the domain. In that case, we have, respectively, a concave or convex, or the same rule as for the matrix of the quadratic forms, okay? So, we can write this here as a, if you like to have a statement about this, we can write just to make the rule a little bit more formal. Consider f of x1, x2 twice differentiable. You know what twice differentiable means? Twice differentiable for a one variable function is that it makes sense to provide a second order approximation. So to approximate a function with a parabola, okay? The same here. A twice differentiable function of two variables is a surface for which it makes sense to provide an approximation with a quadratic form, okay? So this, a twice differentiable function of two variables is a regular surface, very regular surface in the space. If with domain A. If this is the notation for the Hessian matrix, the matrix of the second derivatives, both pure and mixed, which is by definition a symmetric matrix, remember? This is by definition a symmetric matrix. If the Hessian matrix at any point x1, x2 is positive, definite, then we should make this precise. For any point of the domain, then F is strictly convex in its domain. Why are there blank spaces in the definition? Just because if it is negative, definite, then it is, sorry, that this convex should go before. Should go here, the convex, respectively, concave. Strictly holds for both, okay? Strictly convex or strictly concave in its domain. And also, if instead of being definite is semi-definite, okay, then it is just convex. So that's because I want a definition that holds for 4 different definitions, okay? If it is positive definite, the function is strictly convex. If it is negative definite, the function is strictly concave. If it is positive semi-definite, the function is just convex, possibly not strictly, okay? If it is negative semi-definite, it is concave, but possibly not strictly. I mean, the matrix, Hessian matrix, has the same information content as the matrix of a quadratic form, okay? Is that clear? The Hessian matrix of the function, provided that what we see holds for any point of the domain, has the same information content as the matrix A of the quadratic form. Okay? Now, let me just check this for this one, and next we go to the second order approximation. I'm going to explain why this works this way, just showing you how a two-variable function can be approximated by a linear term and a quadratic term, and the quadratic term will be a quadratic form, basically. Okay, so but just look at this example. Okay, look at this function. It is a function of two variables, 1 plus alpha x1 plus beta x2. Alpha and beta are positive. It's not written here maybe, but alpha and beta, I mean, they could be also negative, but I prefer to regard them as positive. Alpha and beta are positive coefficients. Anyway, this is a linear expression in x1, x2. This linear expression, which is a function of two variables, okay, it gives as a result a number. Provided that this number is positive, it's possible to compute the log of this number, okay? So this is a function of two variables. It has a domain and so on and so forth. This is linear. This is a concave transformation of a linear function. Our function y is concave, okay? Because the log is a concave function, one of the most elementary concave functions. If you compute the second derivative of the log of x, you see that the second derivative is always negative, which means that the function is concave, okay? So we have a concave transformation of a number, which is itself a function of two variables, which is linear function. Concave transformation of a linear function, concave, without computing the derivatives. You know that already. But if you like, you can compute the derivatives to check this. And in this case, it is possible to see that the Hessian matrix is negative semi-definite for any x in the domain. Why? Because if you compute the gradient, this is the gradient, so the vector, the row vector, collecting the first derivatives, the first partial derivatives, we did it already for this function. The first derivative with respect to x is alpha divided by 1 plus alpha x1 plus beta x2. The partial derivative with respect to y is beta divided by 1 plus alpha x1 plus beta x2. What are the second derivatives? Pure derivatives, which means compute again the derivative of this one with respect to x1. Okay? So you have alpha divided by a function of x1 and x2, so it is minus alpha divided by the same function squared, okay, times alpha, because the coefficient of x1 is alpha. So you have alpha squared here. For the other corner, you have the pure derivative, pure second derivative with respect to x2, which is similar to this one in structure. It is minus beta squared over 1 plus alpha x1 plus beta x2 squared. What about the mixed derivatives? It means compute the derivative of this one with respect to x2. So you again have alpha minus alpha divided by this one squared, but this time times beta. And also, if you do that by computing the derivative of this with respect to x1, these are the mixed derivatives, which should be equal to each other based on the theory, you get actually the same value as this one. So the matrix is symmetric, of course. The Hessian matrix depends on x1 and x2 in general. But look at what happens here. The two pure derivatives in the main diagonal are both negative. Negative, negative. Why is that? Because the denominator is a positive quantity. Alpha squared, beta squared, positive, whatever alpha and beta are. With the minus sign, they are negative. Now compute the determinant. This times this, minus this times this. The products in the main diagonal and the other diagonal are the same, okay? If you subtract one to the other, you get 0. And this fits with the definition of a negative semi-definite quadratic form. So we can conclude that our function is concave, also based on the study of the second derivatives of the Hessian matrix, okay? In general, these results, concave transformation of a linear function, are not proven using the second derivatives. They can be proven based on the definition, okay? Definition of concavity. We have definitions of concavity related to that geometric intuition of the shape and the segment joining the points and so on and so forth. But of course, what we know in general can be tested also using the Hessian matrix. Clear? So this is one very important example. Now, I'm going to show you Oh, you don't need, okay, I put everything here because to show you the similarities between the two variable formula and the one variable formula, but you already know what is the linear and the quadratic approximation for a one variable function. Now we extend the formulas to a two variable function, okay? So I don't repeat everything. This curve is a one variable function. The tangent line is the best linear approximation to this one variable function. The differential is defined as the product of the derivative at the initial point times the increment h, okay? You know already what the interpretation of the differential for a one variable function is, and the most important formula is this one. So if we have a function of one variable, which is regular, so it is differentiable, we take an initial point, a, we can replace the expression of our one variable function with a linear function of x, which is the equation of the straight line tangent to this curve at the point A. And the equation of this straight line is f of a, which means the value of the function at the initial point, plus the slope of the tangent line, which is the derivative at the initial point, times x minus a, okay? So this is the linear approximation to f of x. If you remember, we already defined the differential for a two-variable function. Let me just show you what is the quadratic, recap what is the quadratic approximation. We can improve the linear approximation by adding a quadratic term, okay? So this one will be the same, but we will add a quadratic term. In fact, this remains the same, and the quadratic term is 1/2 times the second derivative at the initial point times x minus a squared, okay? Now, remember these formulas and try to keep them in mind for one variable functions, because for two variable functions, they are exactly the same, provided that you use matrix notation. So if you use the matrix notation, you get exactly the same formula, but this will not be the derivative because we have a gradient for n variable functions, and this will not be the second derivative because we have the Hessian matrix, okay? And the squared will be replaced by a quadratic form. Now, this is again, I'm trying to recap what we already did. I want to show you a couple of things here. You may, it's, for me, personally, it is impressive. You know that we can improve and improve again our approximation by using third derivative, fourth derivative, fifth derivative, until we arrive at so-called Taylor approximations of any order, okay? And in principle, in many cases, a Taylor approximation of a very large order is something very, very similar to the function, not just at the point, but also very far from the point, okay? And this is impressive to me because what we use is only the information at the initial point. In order to provide the approximation, we assume a given x away from the initial point, but we use only the coefficients, only summarize the information that we have at the initial point, okay? But you can arrive at any approximation by looking at the slope, at the concavity, and at the third order, fourth order, let's say, curvatures of the function. Near the point, you can arrive at very good approximation, also very far from the point. Closed. For the two variable case, the point is defined by two coordinates, but we can move along any direction away from this point, and we have the differential of the function, which is basically again given by the gradient times the vector of the increments. You have already this formula in your notes, I guess, because I already explained this, which means if you look at the vector notation and you remember that this is a row vector, and you remember the product between a row vector and a column vector, you have to multiply the two vectors element by element, okay? So it is the partial derivative with respect to x1 times h1 plus the partial derivative with respect to x2 times h2, okay? Which means gradient times h, and here we have derivative times h. Gradient times h is the same. Linear approximation. F of x can be approximated linearly by f of a plus gradient times x minus a. Exactly as in the case of the one variable functions, okay? F of x is equal to f of a plus derivative times x minus a. It is the same formula. Of course, what is this one? Can we write this extensively, explicitly, without using the matrix notation? It would become f of a1, a2, which means the value of the function at the initial point, plus the partial derivative with respect to x1 at the initial point, times the increment, x1 minus a1, plus the partial derivative with respect to x2, times the increment, x2 minus a2. So this is the meaning of this. What about the quadratic approximation? Remember that the first part is the same, it is the linear one, and then we have the additional quadratic term is 1/2, I would say, times second derivative times x minus a squared. We don't have x minus a squared with the matrix notation, we have a quadratic form. X minus a transpose times Hessian matrix times x minus a, okay? Which is the equivalent of having squared for a having x minus a squared for a one variable function. This is a quadratic form of the type h transpose times h times a times h, where a, our matrix A, is the Hessian matrix of the matrix at the initial point. So this is the main point. It is a quadratic form in which the Hessian matrix computed at the point plays the role of the matrix A for quadratic forms, for the basic definition of quadratic forms. So the matrix that characterizes the quadratic form in this case is the Hessian matrix. Clear? Can we solve a simple example, numerical example? Of course, in general, these will be computationally more challenging than just computing the first order approximation, but we can provide a numerical example. Not of the computation of the, I don't want to compute to have the expression of the quadratic approximation as a function. I want to approximate to the second order the increment of the function, or the value of the function at a new point, using, of course, this expression with a specific x, okay? This is what I want to do now. This is the same function as before. We know already what the gradient and the Hessian matrix is for this function. Both the gradient and the Hessian matrix at a given point take specific numerical values. Now I select values for the parameters. Alpha is 1/3, beta is 1/5. I want to approximate to the first order and then to the second order f at the point 0.15, 0.2, and to provide this approximation near the point 0, 0, means compute the value of the function, not using the formula of the function, but using the first order and the second order approximations near the point 0, 0, because the approximation changes when you change the initial point, okay? You have to specify an initial point when you want to approximate a function. Clear? Okay, so what is the value of the function at the initial point 0, 0? The log of 1 plus 0 plus 0. The log of 1 is 0. So the value of the function at the initial point is 0. Next, we have the expression for the gradient. In the previous example, this one. If you put here the parameters, which was 1 over 5 and 1 over 3, I guess, and now you put here 0 and 0, you get the numerical value for the gradient at the point and the numerical values for the Hessian matrix at the point. And they are like this: minus 1 over 9, minus 1 over 15, minus 1 over 15, minus 1 over 25. Okay? I just replaced alpha and beta equal to these values because we have parameters. And 0, 0 to x1 and x2 in the previous matrices, in the previous matrix for the Hessian. The true value of the function, can compute the true value by just putting 0.15 and 0.2 here, is this one, 0.086178. If you provide a first order approximation, you use this formula. Okay? Remember that the initial point A is 0, 0, while x is 0.15, 0.20. Okay? It's a vector. So what is the first order approximation? It is the value of the function at the initial point plus the first element of the gradient, 1/3, times the increment of the first variable, which is 0.15 minus 0. So in this case, it is 0.15. Plus the second element of the gradient, 1 over 5 times 0.2, and you get 0.09. Okay? 0.09 will be necessarily an excess approximation. Why? Because when you have a concave function, and you take the first order approximation, you take the approximation along the tangent plane. But since for a concave function, the tangent plane lies above the surface, if you move away from your initial point and you use the plane instead of the surface, clearly you overestimate the change. So our second order approximation will make a correction for this bias, okay? Why is that? It's clear. Since this is concave, the quadratic form that characterizes the second order term is negative definite. Clear? So it will reduce. It will be something negative. It will reduce the value that comes out from the first order approximation. In fact, if we try to compute the second order approximation, we have 0.09, which is the first order approximation, because it is always a term which is present also in the second order approximation, plus, so this is the full expression for the quadratic form. Remember, it is the coefficient A11 times the first increment squared plus twice the mixed coefficient in the matrix, which is this one, twice the mixed coefficient, which was minus 1 over 15, times the product of the two variables, that is the product of the two increments, of the first variable and the second variables, plus the coefficient A22 times the second increment squared. If you add this to your first order approximation, you get a much better approximation to your function, okay? I guess this example should make clear a lot of different features of this second order approximation. What really matters to characterize basically the concavity or the convexity of a function near a point is whether the Hessian matrix is positive definite or negative definite at that point. If this happens at any point of the domain, you clearly have a convex function or a concave function. This is based on geometric intuition, but it should be proven, of course, but it is very intuitive, okay? So this will be the tools that we will also use to show, for instance, that are used to show that concavity and convexity are important for characterizing local maxima and local minima for a two-variable function or for an n-variable function. Okay, so this is part on. I tried in the examination. I will not ask you to solve numerically second-order approximation. So for one variable functions, that's okay. But this will be focused on two variables and n-variable functions. So this is in general challenging computationally. It takes time. It is also a source of possible computational mistakes, errors. I prefer to avoid it, but it is important for me that you understand the structure of these products. Of course, I could ask you to compute a quadratic form, for instance. Okay, so that, but not approximating a two-variable function with a quadratic form. But first-order approximations of two-variable functions are part also of the written examination. Okay, so first-order approximation could be a question. Okay. And first-order approximation just means using basically the gradient. Okay, so this is an example. Now, let me continue with unconstrained optimization and examples. Okay. Let me just introduce some basic concepts and then show you the examples in the next part of this lesson. And these concepts are basically global and local maxima and minima for an n-variable function. So the first slides are only definitions. We must understand the definitions. So, which kind of objects or concepts are these, okay? Okay, so let me define what is a maximum point or a minimum point, symmetrically, for a function of n variables, y equal to f of x. X is a vector. First of all, a maximum point or a minimum point are points of the domain of the function, okay? The problem will be finding the points of the domain of the function which maximize or minimize our n variable function, okay? So our choice problem is selecting the points of the domain by which a certain function that depends on the variables of this domain is maximized or minimized. So remember that when I say maximum point, minimum point, it is a point of the domain. When I just say maximum or minimum of the function, this is the value of the function corresponding to the maximum point of the domain or to the minimum point of the domain, okay? So we basically want to find the maximum, for instance, of a function by identifying what is the maximum point of the domain. Okay, so this is the first, so don't get confused. The minimum, sometimes students say, okay, the question could be, what is the value, what is the maximum corresponding to this optimal value? And the maximum answer is the maximum is in fact the maximum point. No, the maximum point is a point of the domain. If I select that point of the domain, I get my function maximized, okay? Definitions. I have x star here in this definition, which is a point of the domain. X star is a vector, so it's made up of n components, x1, x2, xn star. What is the meaning of this statement? X star is a global maximum point for my function. Or alternatively, X star is a global minimum point for my function. Okay, the green definition corresponds to the green formula here, okay? X star is a global maximum point for my function, not necessarily the global maximum point, a global maximum point. There could be many of them if the value of the function at any other point of the domain is less or equal to the value of the function at the maximum point, okay? At the point X star. That is, if at the point X star my function takes a value which is not smaller than the values that the function takes at any other point of the domain, this is a global maximum point for my function. Clear? Respectively, if I focus on the minimum, okay, X star is a global minimum point if at any other point of the domain function takes on a value which is not smaller, which is greater or equal to the value at the point X star. Clear? So it's just a matter of reversing the inequalities. And this is the definition of global maximum point and global minimum point. So what is a global maximum? Global maximum is the value of the function, is the value of the function corresponding to the global maximum points. What is the global minimum is the value of the function corresponding to the global minimum points. Remember, why is there can be many global minimum points, but only one global minimum? Remember the example of that quadratic form, positive semi-definite. There is a full line in the plane, so a full line of points in the domain, where the function reaches its minimum, which is 0. So the minimum is 1, which is 0. But the minimum points are infinitely many. Okay? Is that clear? Because there is a full line of points in the domain, but the minimum, based on the definition, is unique because it is a value of the function, which is 0 in this example. Okay? Now, what is the definition between global and local? I want to be clear here. I will focus on global, not on local, because in 95% of the examples, you will have global maximum points, global minimum points, okay? The problem will be finding them, but you will be sure that these are the global maximum point or the global minimum point. Local is the same definition as above, but instead of saying that these properties hold for any point in the domain, we say that these properties hold at least for any value of the domain near our supposed point X star, okay? So basically, if you, I don't want to try to provide pictures in two-dimensional case, but if you look at the one-dimensional case, which is of course also included in that definition. So here you have a global minimum and a local minimum which is not global. Think of the definition. This X star for this function is a global minimum point because if you select any other point of the domain, the value at any other point of the domain is not smaller than the value here. Okay? Clear? This is a local minimum point, but not global, unfortunately. Just because you can apply the same definition, but you don't have to say if I select any other point of the domain. Okay? Because that's not true. If you select a point here, this doesn't hold. But you must say if I select other points of the domain that are close enough to our supposed minimum point, then that property holds, okay? So there is a more formal definition, if it is possible, to identify a neighborhood of the point such that that property holds for any point of the neighborhood. A neighborhood is an interval including the point, okay, in one dimension. I prefer to give the definition using the word near, which is not, it is mathematics. Near is mathematics because it can be made rigorous, okay? But it is also very intuitive. At least for x near x star. But the property is the same as above, okay? The maximum, or respectively the minimum of the function, is denoted by y star, which is f of x star. Okay, we don't need to provide the example with one variable. Remember that we are dealing with also another property. We will deal only with global maximum and global minimum points, and we will deal with points that x star that are interior to the domain, because another possible issue arises from the possibility that x star is a boundary point of the domain. If you look, but we will not deal with this issue. Look at this. Suppose that the domain is from here to here, okay? Here you have, this is a global maximum point. X hat is a global maximum point. X tilde is a local minimum point. X star is a local maximum point, and the upper bound of the interval, which is x with this reversed hat, is a global minimum point. Can you see it? Based on the definition. However, this one and this one are boundary points of the domain. They are not interior. So what I'm going to say next doesn't apply to them. Okay? So we will only deal with global maxima, global minima that are interior to the domain, not on the boundary, in case our domain is a closed set. Okay?
Excuse me, Professor.
Sure.
Can you repeat, please, why we cannot compute at the at the boundary?
No. I didn't say that we cannot compute, that we cannot consider what happens in the on the boundary of our domain. We must do that if we have a problem in which the domain of choice is a closed set. We must do that. But what I'm going to say next, this theorem only applies to those global maximum or minimum points that are interior to the domain. So what we do when we have also the boundary to be considered for our problem is to apply this, find the candidates that are interior, and then check the behavior on the boundary as another part of the problem, and see whether moving the point on the boundary, we can improve our function further as compared to what we already know for the interior points, okay? Is that clear? So this result applies only to the maximum and minima that are interior. Is that clear?
Yes, thank you.
Okay. And next, I will show you immediately why, in this case, it doesn't apply to the boundary point, of course. Okay, so the main theorem is that if our function is differentiable, this holds for any number of variables, also for one variable. If our function is differentiable and x star is an interior local maximum or local minimum point, then necessarily the gradient at this point is 0, okay? Remember the one-dimensional case. In the one-dimensional case, this would read, if f is differentiable and x is an interior local maximum or minimum, then at that point the derivative is 0. So the tangent to the graph at that particular point will be parallel to the x-axis, will be horizontal, okay? So this is called a necessary condition for an interior local maximum or minimum of a differentiable function. Of course, this holds only for an interior point. Because if you look at the boundary here, clearly this is a maximum, which is global. If it is global, it is necessarily also local, by definition. But here the derivative is not zero, because the slope is negative. Also here the derivative is not zero, because the slope is negative. And this happens, this is possible because we are on the boundary. So look at this, this is called the necessary condition or first order condition for a maximum. You always apply this if you study a little bit of mathematics or study of a function in the high school, for instance. When finding the maxima or minima for a function, compute the derivative, set the derivative equal to 0, you have an equation, you find the points, and these are the candidates to be maxima or minima. But they can also be inflection points with the horizontal tangent, for instance, okay? Next, further tests are needed. Second derivatives test. Is that a maximum? Is that a minimum? So forget about these things here, because we have functions that have basically only a global maximum or a global minimum. But of course, this result is important to stress the next one. So if we add the property of concavity or of convexity, then this theorem becomes much more powerful, okay? We know that this condition, which is this one, gradient at the point equal to 0, is a necessary condition for a local maximum or minimum for the function at the point x star. Necessary means that if the point is a maximum or minimum point, then, and it is interior, and the function is differentiable, then this condition necessarily holds, right? This is the meaning of maximum or minimum, of necessary condition. This is not sufficient. You know the difference between a sufficient condition and a necessary condition. This is not sufficient, it's only necessary. A necessary condition can be used in a negative fashion. So what we do, for instance, is compute the first derivative. Remember the study of a function, compute the first derivative, set the first derivative equal to 0. We have some points as the solution. They're the candidates, maximum and minimum. This means that you can exclude all the other points. So we use the necessary conditions in a negative fashion to exclude something, but it is not sufficient. But if we add the property that our function is concave, then this condition, gradient equal to 0, is not only necessary for a local maximum, it becomes sufficient for a global maximum, okay? So this is the power of concavity. The same condition, gradient equal to 0, becomes sufficient for a global maximum if we add concavity to the previous theorem in the assumptions. Similarly, if we add the assumption of convexity, if we know that our function is convex, then gradient equal to 0 is a sufficient condition for a global minimum. So basically, our way to deal with this function, because next there are 1, 2, 3 examples, 4 examples that are really important. They are very typical, starting from the simplest possible examples to something which is more difficult in general. So what I want to point out here before just 1 minute before the break is that our way to solve these exercises will be like this. I will not submit to you problems in which we have local maxima or local minima, okay? Multiple local maxima, multiple local minima, and then try to understand with the second derivatives test whether they are local maximum or minimum. Only problems where we will have one global maximum or one global minimum. But sometimes, because the 95% of the models, the common models in economics are like this, okay? Not only in static optimization, but also in dynamic optimization, you will see the concavity, convexity properties are always present. So you are sure that the first order conditions, if you are able to solve them, they provide you with the solution, okay? So, It will be a matter of solving the first order condition, gradient equal to 0, okay? And then possibly check that this is actually a maximum or a minimum with arguments related to the previous general properties, these ones. You remember the properties to understand concavity, convexity in general, these properties, this list of properties here. Okay, criteria for concavity, the ones seen before. So possibly a question will be to motivate your answer. Why is that a maximum? Why is that a minimum? Okay, because this is convex because it is a convex of two functions that are convex for these reasons, okay? This is the answer, and possibly some additional questions related to how does the solution change if you change the parameters or something like this, okay? So no worries about the presence of multiple local maxima or minima. I don't want to waste time with these very interesting things, but not really common in most in basic problems that you have to understand in this course, okay? So this is now we take a well-deserved break of 15 minutes and see you here in 15 minutes, okay? So we take a break now, 15 minutes break, and we start again in 15 minutes. Okay. Okay, can you hear me? Can you hear me? Is everything okay?
Yes.
Okay, thank you.
Yes.
Let me share, thank you. Let me share the screen again. Like this, and then like this, then like this. Okay, now let me enlarge the screen and go to the examples. Look at these examples start from very similar, very simple, and to slightly more difficult, let's say. Okay, I start today and I will continue tomorrow. I want, the examples are simple, but I want you to get the structure of these examples, okay? To be able to solve more complicated examples, but having the same structure. I focus on structures. Okay, this is the first one. Very simple. Y equal to f of x1, x2 is equal to square root of x1 plus 1/2 square root of x2 minus a coefficient, a positive coefficient, 1/5 times x1 plus x2. Of course, you could as well construct examples with 3 variables, having the same structure. We will see one in the summary, in the examples review exercises. I guess next week. We want to find a global maximum point and to check preliminarily that the point that will satisfy the first order condition will be in fact a maximum point. So we want to check preliminarily that this is a concave function of x1 and x2. Why is this a concave function of x1 and x2? Because remember, first of all, it is additively separable in x1, x2. So this will make the solution very, very easy. It is additively separable because it can be written as a function of x1 plus a function of x2. This is the meaning of additively separable. And not all functions are additively separable. For instance, this one, f of xy equal to x plus 2y plus 1/2 xy is not additively separable. It is very simple, but it is not additively separable in the 2 variables. There is a term in which we have a product, so you cannot write this as something which is g of x plus h of y. It's impossible to get this structure, starting from this. But if you look at the function here, you have a function of x1, which is square root of x1 minus 1/5 x1, plus a function of only x2, which is 1/2 square root of x2 minus 1/5 x2, okay? So this is additively separable in the 2 variables. What is the property of these functions? Very clear. The first derivative with respect to x1 will not depend on x2, and the first derivative with respect to x2 will not depend on x1. While in this case, if you compute the derivative with respect to one variable, this depends also on the other variable. okay? In principle. So there is a cross dependence between the variables also in the derivatives, which is not the case here. You will see in a moment from the gradient. So this means that the system partial derivatives equal to 0 is in fact a combination of two different equations, each in a different variable. So it's not really a system. You have an equation in x, an equation in y, which is really easy to solve. But many problems are additively separable, in fact. Okay, so we want to find a global maximum point. Preliminarily, we want to check that this is a concave function. Sum of, okay, so this is square root of x1 is a concave function of x1, because the square root is one of the most elementary types of one variable concave functions. 1/2 square root of x2 is a concave function of x2, and these are two linear functions of x1 and x2. Linear can be both convex and concave, considered both convex and concave depending on the convenience. They are neutral, basically. They are neutral in terms of concavity. And this means that we have the sum of a concave function of x1. Why? Because the square root term plus the linear term is concave. Sum of two concave functions, okay? The sum of the square root term plus the linear term is concave. So we have a concave function of x1 plus a concave function of x2, which means the sum of two concave functions of both x1 and x2. Almost all the properties listed above are here, okay? A concave function of one variable can be considered also a concave function of two variables. Linear functions are both convex and concave. The sum of a concave function, the sum of two concave functions is concave. So we have three of the above properties here, if you look into this carefully. So this is concave, and this means that if I find a point where the gradient is 0, this is necessarily a global maximum point. Clear? So the problem reduces to the so-called solution to the first order condition. The first order condition means compute the gradient and set the gradient equal to 0. You get a system in which each of the two partial derivatives must be equal to 0, okay? This is a system in general in two equations, in this case, two equations and two variables. You have to solve the system. So what is the partial derivative of this two variable function with respect to x1? Okay, it is 1/2 square root of x1 minus 1/5. This is the partial derivative of my function with respect to x1. The gradient must be equal to 0, so in particular each partial derivative must be equal to 0. So this must be equal to 0. The partial derivative with respect to x2 is 1/4 square root of x2 minus 1/2 again, and this must be equal to 0. So we have a system of two equations in two variables, but very trivially, each equation is in fact an equation in a unique variable. So we can solve the equations separately. From the first one, we have that 2 square root of x1 is equal to 5, okay? From the second one, we have that 4 square root of x2 is equal to 5 as well. Can you see that why the solution is so easy in this case? Is it difficult to write down this, moving from this one to this one? Is that clear? Okay. And this means that x1 is 5/2 squared, so it's 25/4. And x2 is 25/16. So this is the global maximum point. This is the point at which my two-variable function reaches the highest level which is possible by selecting the variables in their domain, and in particular the domain here clearly is any value of x1 and x2 which is non-negative. Okay? Clear? Because we have a square root, let's say, square root issue that restricts the domain to the positive values of x1 and x2. Okay. This is the global maximum point. What is the global maximum? So what is this highest possible level that the function reaches corresponding to the maximum point? It's just a matter of replacing these optimal values into the function. So it will be the square root of 25 over 4, which is 5 over 2, plus 1/2 square root of 25 over 16, which is 1/2 times 5 over 4, minus 1/2 x1 plus x2, so this plus this, okay? Then we perform the computations, we simplify everything, and we get that the highest possible value of the function is 25 over 16. So this is the most trivial example that I can imagine. Actually, there is another one in which, that this will be maybe tomorrow, in which I will show you that actually when we maximize a quadratic form, a negative definite quadratic form, we get a Hessian matrix, which is matrix A that characterizes the quadratic form, okay? So that will be an example to show that. But apart from that, this is the easiest example in two variables that I can really imagine, okay? Additively separable, elementary function, square root, and linear. Second example. Now, there is already something to learn here. Here you see already, apart that each equation depends on a unique variable, but here you see already a solution, which is a technique which is very common, which is trying, in general, here you will get an expression that depends on two variables in general, and also here, an expression that depends on two variables, equal to 0, equal to 0. So one very fruitful technique to solve this is to try to get on the right side the same quantity, okay, and here on the left, an expression that depends on two variables, here and here. If the quantity on the right-hand side is the same, also the left-hand side must be equal to each other, okay? This is one very useful technique. We don't use it here because it's trivial, but in general it works. Now, look at this function. F of xy is the log of 1 plus 10 times x plus 2y minus x plus y squared. First of all, we want to find the maximum, okay? It's not written here, but we want to find the maximum of this function. So a preliminary question is, why do we use only the first order condition? Are we sure that this function is concave? Okay? So try to figure out why this function is concave. Term by term, and then possibly we apply the result by which the sum of concave functions is a concave function, okay? Look at the first term. It is a function of only x. By the way, this is no longer an additively separable function in x and y. Why? Because in this term here, there is x squared plus y squared plus 2xy. The product between x and y no longer additively separable, okay? Look at the first term, it is a function of only x. Is that a concave function of x? The argument of the log is linear, and the log is a concave, elementary function of one variable. So a concave transformation of a linear function is concave. Okay? This is one of the criteria listed above. Concave transformation of a linear function. By the way, this is a concave function of x and also a concave function of x and y, okay? Because a concave function in one variable can be regarded as a concave function in two variables or n variables as well. 2y is linear in y, so it is concave. It is neutral, so it doesn't affect the concavity of the sum of these two. The sum of these two is concave because it is the sum of two concave functions of x and y. Clear? What about this? X plus y squared. Try to expand this. X squared plus 2xy plus y squared. This is a quadratic form. So by exercise, you should try to understand what is the matrix associated to this quadratic form. X plus y squared, you can prove it very quickly by looking at the matrix, is positive semi-definite. X plus y squared is positive semi-definite. So it is convex, but it's negative. The negative of a convex function is concave. Okay? These are the three logical steps that allow us to conclude that the sum of these three is concave. They will be summarized in the next slide here. Now we are sure that this is a concave function of x and y. If we find a point in which the gradient is zero, this is the global maximum point. Again, this reduces to finding the solution to this system of equations in x and y. Compute the derivative of our function with respect to x. Derivative is 1 over the argument of the log times the derivative of the argument with respect to x times 10. And this is the derivative of the first term with respect to x. The second one is 0, the derivative, because it depends only on y. What about the third one? Don't expand this square, just use the chain rule. So minus 2x plus y times the derivative with respect to x of the base of this power, which is 1, okay? So minus 2x plus y, and this must be equal to 0. Partial derivative with respect to y, this becomes 0, this is 2, and this again is minus 2x plus y. Is that clear? Okay, equal to 0. Now, what you should not do now is trying to obtain from the first equation x as a function of y, or y as a function of x, and then replace into the second equation. This is, I mean, a common way and a correct way to solve linear systems if you don't know the matrix solution formula. But not, in general, this is not very useful if the system is nonlinear, like in this case. What we should try to do is to work out this equation in order to have the same quantity on the right-hand side, which allows us then to impose the equality between the corresponding left-hand sides, okay? Sorry for explaining you these things that should belong to the high school, but I find that it's really useful to look at the structures also of the practical solution of these equations, because they happen very often. So what we can do here is to solve immediately this equation, not for x or for y, but for the aggregate quantity x plus y, which appears also here, okay? So what is, we don't know what x is, y is, but we know for sure what x plus y is. It is equal to 1, okay? Because if I move this to the right and I divide both sides by 2, it is x plus y, equal to 1. So I know that the sum of the two variables in the solution is 1. Now, here I have the sum, so I replace with 1. Okay? And this first equation becomes 10 over 1 plus 10x is equal to 2 on the right. I divide both sides by 2, and I have 5 divided by 1 plus 10x is equal to 1. Okay? Since both this one and this one are equal to 1, this must be equal to this. Okay? Okay, so that would be one strategy, and the other strategy is also, so I could write this equal to this, but since x plus y is equal to 1, I would get precisely what I get here, okay? So if this is equivalent to solve this, and then to replace the solution into this one and to solve for y, okay? So there are many ways. So having the same quantity on the right and then equating the quantities on the left is one strategy. In this case, it is even easier because this is equal to 1. Okay, so it is already here. It is already here. But it is very useful in general. In this case, we get a first equation which depends only on x. We solve this for x. It is 1 plus 10x is equal to 5. So x is equal to 2 over 5 because this is a linear equation in x. I replace the equation by substitution. I replace the solution for x here. 2 over 5 plus y is equal to 1. 1 is equal to 3 over 5. Okay? And the function is concave, so this solution is the global maximum. So what I recommend in this case is don't expand this. Try to solve compute the derivatives and preserve the sum here without expanding this square. And then don't try to obtain here x as a function of y or y as a function of x from the first equation and then replace in the other one, because things become more complicated in this way. You get the solution, but the probability of a mistake is higher. Why is the function concave? The log of 1 plus 10x is a concave transformation of an affine function, so it is concave. 2y is linear, and therefore it is concave. X plus y squared is positive semi-definite, so it is convex, and its negative is concave. So we have the sum of 3 concave terms. Our function is concave.
Excuse me.
Yes?
What do you mean by concave transformation?
A concave transformation means a concave function of. Okay, so it is a concave, where is it? Concave function of an affine function. A function can be also called a transformation because a function transforms the independent variable or the independent variables into something different, okay? So you apply a transformation to get a result, which is the dependent variable. So it's just another word to say function. Clear?
Yes, thank you.
Okay, welcome. My suggestion is to check for concavity of the function here, not by using the general criteria that we use now, but by using the Hessian matrix, and check that the Hessian matrix is negative semi-definite, or maybe even negative definite, for any x in the domain. Okay? Oh, sorry. Thank you. Okay, so this is a useful exercise. I mean, if you can't make it with the general criteria in at least 50% of the cases, you will be able to look at the second derivatives and to conclude that for any x in the domain, the Hessian matrix is, in this case, negative semi-definite or negative definite, okay? I don't know because I didn't try, but they are elementary functions, so very easily you will find that it works. But looking at general criteria would be much better, because imagine that instead of having the log of this, we have the square root of the log of this plus 5, okay? So it's a nested structure of concave transformations, okay? So it is very easy to detect with our general criteria, less easy to be checked with the second derivatives. Clear? Okay. Third example, really easy, but a source of infinitely many possible types of mistakes, but really easy, actually. Okay, so this is a very classical example. If you suppose that, if you assume that X and Y represent the input quantities of two production factors, and you suppose that F is a production function transforms the amounts of the input into the amount of the output, okay? So capital F of xy is the output that we obtain by putting into the production process x units of the first input factor and y units of the second input factor. Usually output is in terms of physical quantity, okay? If I suppose that I can sell all the output at a given price P, this is the revenue, okay? Quantity of output, all sold out at the price P, okay? This is the revenue. This is a cost function in which the amounts of the input are here, and this is the cost of production corresponding to X units of first input and Y units of the second input, the variable cost, for instance. So the revenue minus the cost is the profit, okay? Very simple, basic model, two variables. Okay. Now suppose, very typically X and Y are strictly positive quantities. F of X and Y could be, for instance, this function, the cubic root of the product xy, which is one possible Cobb-Douglas function, which is very common for production functions. And the cost could be, for instance, linear. This is a very common specification of the cost function because we have a unit cost, for instance, 1 for the input factor, for the first input factor. So if you use 8 units of the first input factor and the unit cost is 1, you have 8 of the cost. The cost is 8. If the unit cost of the second input factor is 2, 2y is the part of the cost that corresponds to the second input factor. So very common linear function. But it could be also nonlinear if if the cost depends on the quantities used, if the unit cost depends on the quantities used, this could become a nonlinear function, okay? Suppose that the unit price is 3, so what is the profit in this case? Is 3 times xy to the power 1/3 minus x minus 2y. Is that a concave function? The answer is yes, because here we have a Cobb-Douglas function with the sum of the exponents, which is 2/3, and we know that a Cobb-Douglas function is concave if the sum of the exponents is less than 1, okay? Then we will prove this based on the second derivatives, but this will be just an exercise, a very simple exercise. Times 3, so times a constant doesn't change the concavity, of course, the property is the same, minus a linear function.